a vast silicon foundry floor bathed in cool blue light. Massive EUV scanners looming like monolithic sentinels. Their chambers humming with contained plasma. Imagine standing at the edge of a silent cathedral where the altar is not stone but a wafer of pure silicon. Each layer etched with the fury of ultraviolet light born from laser-driven tin plasma. The air thrums with a tension that feels less like machinery and more like the restrained breath of a giant about to exhale. Here the promise of artificial intelligence hangs on a thread thinner than a virus. A thread that is pulled not by the roar of graphics cards, but by the whisper of atomic-scale processes that few can see and fewer still can master. The first whisper comes from the extreme ultraviolet source itself, a heart that beats at the edge of what physics allows. Inside its chamber, a laser strikes a droplet of tin, creating a plasma that emits photons at a wavelength that can draw features smaller than a strand of DNA. Yet this heart is strained. The plasma struggles to stay stable as it tries to push more energy out. And the collector mirrors that gather those precious photons begin to erode under the relentless barrage of high-energy ions and debris. The result is a ceiling on how much power can be coaxed from the source without triggering a cascade of instabilities that would scar the optics and halt production. To nudge this ceiling upward demands not just a stronger laser, but a complete reorchestration of tin delivery and debris mitigation. Each element intertwined like the threads of a spider's web, where pulling one tightens the others. The cost of each incremental gain climbs exponentially, turning what should be a steady march towards smaller nodes into a steep cliff that only a handful of engineers equipped with deep plasma diagnostics and radiation-hardened optics can even approach. Close-up of a tin droplet illuminated by a pulsing laser. Plasma flaring inside a vacuum chamber. Collector mirrors showing subtle pitting because the source cannot simply be turned up. The number of wafers that can be processed per hour drops, and the yield of each EUV-exposed layer suffers. Every % of lost power translates directly into a higher cost per layer, a cost that is then amplified as dozens of layers stack to form the logic cores that drive today's AI accelerators. Foundries, beholden to this yield wall, begin to ration exposure slots, stretching lead times and inflating prices for the very chips that promise to train the next generation of models. Faced with scarcity, retreat to older nodes, sacrificing the performance per watt gains that newer nodes would have offered. And the entire ecosystem feels the drag of a bottleneck that is invisible to the end user, yet palpable in the data center's power bill. The monopoly here is not a brand name, but a mastery of plasma physics and collector survivability. A knowledge base that lives in the proprietary calibrations of a single supplier who has spent years taming the tin laser interaction, refining the magnetic field configurations that confine the plasma, and engineering coatings that resist ion bombardment. Any challenger attempting to replicate this capability must climb a multi-billion-dollar R&D cliff, rebuild entire beam lines, and survive a qualification timeline that stretches beyond the product cycles of the AI market itself. A sprawling cleanroom corridor. Engineers in bunny suits monitoring banks of diagnostic sensors. Readouts showing plasma stability metrics shift your gaze now to the interposer, the silent bridge that stacks logic dies and memory cubes into a three-dimensional city of silicon. Here the challenge is not light, but heat. The interposer's thermal resistance becomes a hard ceiling as power density climbs. The temperature gradient across the stack steepens, inducing warpage that pulls the bumps out of alignment and creates microscopic cracks that blossom into defects. The result is a yield drop that is not linear but accelerates once the temperature rise exceeds a threshold where the silicon's expansion coefficient clashes with the underbump metallurgy. To push this thermal envelope requires more than just thicker copper pillars. It demands a symphony of material science and thermal engineering. Proprietary underbump cooling layers, engineered with nanostructured interfaces that enhance phonon transport, must be married to advanced simulation toolchains that can predict hot spots at the scale of a few nanometers. Only a handful of firms possess the recipes for these barrier layers. The expertise to tune the annealing cycles that relieve stress without inducing intermetallic growth, and the capability to embed microfluidic channels directly within the interposer substrate. Their advantage is self-reinforcing. Higher yields lower the cost per stacked die, freeing capital to invest further in thermal R&D, which in turn widens the gap with any would-be competitor who lacks the deep toolchain integration and the proprietary material libraries that make the difference between a functional stack and a warped wafer. A cross-sectional view of a 3D stacked package. Heat flowing through microbumps. Color-coded temperature gradients showing hot spots now turn to the humble copper pillar, the tiny conduit that carries signals and power between die and package. As the diameter of these pillars shrinks to enable finer pitch, the cross-sectional area diminishes, and the intrinsic resistivity of copper begins to rise due to surface scattering and grain boundary effects. At the same time, the reduced cross-section accelerates electromigration, the drift of copper atoms under high current density, and stress void formation, where tiny vacancies coalesce into cracks that can open under thermal cycling. Each of these phenomena erodes signal integrity and threatens the reliability of high-speed I/O links that must shuttle multi-gigabit streams between logic and memory. Mastery of this scaling challenge is not a matter of simply choosing a different metal. Alternative conductors such as cobalt or ruthenium face integration hurdles, unknown long-term reliability, and the need to re-qualify entire deposition and etch processes. The few suppliers who dominate this space have refined barrier layers that prevent copper diffusion into the surrounding dielectric, optimized annealing schedules that recrystallize the pillar grain structure to reduce resistivity, and developed pulse plating techniques that achieve uniform filling even at sub-5 micron diameters. Their control extends to the equipment recipes that dictate the precise plasma chemistry and bias conditions during etch, ensuring that pillar sidewalls remain vertical and free of residues that could seed voids. Any attempt to bypass this limit would require a complete overhaul of the plating baths, a redesign of the dielectric stack, and a recharacterization of failure modes that would take years and billions of dollars to validate. A top-down view of a copper pillar array. Pillars shrinking in size. Inset showing atomic scale grain structure and barrier layer, these 3 choke points source power, interposer thermal flux, and pillar resistivity are not isolated obstacles. They form a cascading barrier where each amplifies the others. A weaker EUV source forces foundries to run fewer wafers, which raises the cost per die and reduces the budget available for thermal interposer research. A hotter interposer limits how many dies can be stacked, which in turn increases the I/O density demanded of each copper pillar, pushing them closer to their scaling limits. Improvements in pillar reliability allow higher I/O bandwidth, which can ease the pressure on memory stacking, but only if the interposer can evacuate the extra heat and the lithography can pattern the finer features needed for those pillars. EVER commands the synthesis of plasma stability, thermal transport, and nanoscale metallurgy, holds a set of levers that can tilt the entire AI compute landscape. The next supercycle will not be won by the fastest GPU alone, but by the invisible hand that governs how many photons can be drawn, how much heat can be siphoned, and how reliably electrons can traverse the tiniest of bridges. The question that hangs in the air is not which company will release the next chip, but who will master these gates and thereby dictate the pace at which artificial intelligence can grow. A sweeping aerial view of a silicon fab. Rays of light converging on 3 narrow gates etched into the floor, each gate glowing with a different hue: plasma blue, The narrative now turns to the tightening feedback loop that has begun to reshape the economics of artificial intelligence infrastructure, where each incremental gain in computational density exacts a steeper penalty on the underlying silicon foundation. As transistor densities push toward atomic limits, the heat generated per unit area climbs, and the interposer tasked with spreading that heat must operate ever closer to its thermal ceiling, a ceiling defined by. When the interposer approaches this ceiling, the temperature gradient across the stack rises, increasing thermal resistance and forcing the power delivery network to operate at higher voltage swings to maintain signal integrity, which in turn raises thermal budgets, restrict the number of active layers that can be stacked, thereby reducing the effective I/O bandwidth per unit area and demanding ever finer pitch interconnects to compensate for lost connectivity. The pressure on interconnect pitch pushes the copper pillar geometry toward dimensions where surface scattering dominates electron transport, raising resistivity and exacerbating. Unless advanced barrier alloys and atomic layer deposited liners are employed to suppress diffusion pathways, only a handful of equipment vendors possess the proprietary electroplating recipes and in-situ metrology tools capable of monitoring nucleation kinetics at these scales, giving them leverage over the yield curve of advanced packages. Yield losses in the pillar layer translate directly into lost die per wafer, and because each wafer run already carries a high fixed cost from EUV exposure, the effective cost per functional die rises disproportionately as yield drops below the 70% threshold, often cited as the break-even point for high-volume AI accelerators. The EUV source itself sits at a similar inflection to increase pulse width or reduce repetition rate, both of which cut wafer throughput to push source power beyond 400 watts. Suppliers must lock in high-purity tin supply chains, develop collector coatings with superior resistance to tin redeposition, and refine laser pulse shaping through proprietary plasma physics models that are closely guarded trade secrets. These technical barriers create a natural monopoly. Only those who master the interplay of laser intensity, droplet timing, and collector survivability can guarantee the repeatable exposure doses needed for sub-2 nanometer patterning, and any competitor attempting to replicate the process faces steep yield penalties and extended ramp-up times. The resulting concentration of EUV capacity means that foundries allocating wafer starts must negotiate long-term supply agreements with the incumbent source provider, effectively locking in a portion of their capital expenditure to a single vendor and raising the barrier to entry for new entrants. Turning to the interposer, recent designs embed microchannel coolant networks directly within the dielectric layers using high thermal conductivity materials such as silicon carbide or diamond-like carbon to transport heat away from hot spots before it can diffuse into the active silicon by increasing the cross-sectional area of the coolant pathways and optimizing the channel geometry through computational fluid dynamics simulations. Engineers have demonstrated a greater than 50% increase in allowable heat flux without adding to the overall package thickness. This thermal headroom permits designers to stack additional memory dies or logic layers, thereby reducing the effective EUV exposed area per function and lowering the photon budget required. For each accelerator block, the gain in stacking density is protected by a stack of patents covering the specific material interfaces, the deposition processes for the high conductivity dielectric, and the layout rules that dictate minimum spacing between coolant channels and signal traces, making reverse engineering costly and time-consuming for rivals. Simultaneously, advances in copper pillar metallurgy introduce alloy barriers such as copper manganese nickel and atomic layer deposited liners that inhibit copper diffusion and suppress the formation of intermetallic compounds at the pillar underbump interface. These modifications shift the electromigration lifetime curve upward, allowing reliable operation. They enable scaling down to 3 micrometer pitch with a projected 10-year mean time to failure exceeding the Typical product life cycle: the pillar recipes are locked behind closed-door electroplating baths whose composition, temperature profile, and agitation speed are tuned through design of experiments that only a few tool vendors have fully characterized, and that in situ metrology relies on X-ray fluorescence and acoustic resonance techniques that provide real-time feedback on void fraction and grain structure. When the interposer can evacuate more heat and the pillars can sustain higher current, the combined effect is a step function increase in bandwidth density. Each millimeter squared of package can now carry more data lines without violating thermal or reliability constraints. This bandwidth uplift directly feeds the AI accelerator core, allowing larger tensor cores or more extensive memory interfaces to be fed without stalling, which translates into higher floating point operations per second per watt and a better performance per dollar metric. The synergy is evident when we consider the energy balance. A reduction in thermal resistance lowers the cooling power needed for the data center rack, while the increased I/O efficiency reduces the number of redundant data moves required to keep the compute units saturated. Consequently, the total cost of ownership for an AI workload drops, not only because the silicon itself is cheaper per operation, but because the infrastructure surrounding it, power delivery, chiller capacity, and floor space, can be sized smaller. Market analysts have begun to assign a moat premium to companies that control these three levers: EUV source power, interposer, thermal budget, and pillar-scaled interconnects, mirroring the valuation multiples observed during the period when a single GPU architecture dictated the cadence of AI progress. Investors now look for long-term supply contracts, exclusive access to process design kits, and preferential wafer allocation as indicators of durable competitive advantage, much like they once scrutinized GPU architecture roadmaps for signs of sustained leadership. The strategic implication for AI firms is twofold: either secure early access partnerships with the monopolists to guarantee first silicon advantage, or invest in alternative pathways that bypass the choke points altogether, such as photonic interconnects or heterogeneous integration schemes that rely on optical buffering rather than electrical pillars. For those who choose the partnership route, the payoff includes guaranteed access to the latest source upgrades, early preview of interposer, thermal modules, and co-development of pillar recipes that are tuned to the specific power envelope of their AI models. This early access translates into higher yields, lower per die cost, and the ability to tape out larger dies sooner, giving a performance lead that can be monetized through premium pricing or expanded market share. Conversely, firms that rely on off-the-shelf components find themselves subject to the vagaries of supply allocation, often receiving lower priority during capacity crunches and facing longer qualification cycles for new process nodes. The resulting performance gap widens over generations as each